Hello everyone, welcoming you to Saurabh Sir's classes. Today we are looking at the General Economics paper of the IES 2022 and we are at question number 2. So consider the two variable linear regression model yi equals to alpha plus beta xi plus ui where I goes from 1 to n, where the notations have their usual meaning. Estimate the parameters alpha and beta by the OLS method and also estimate the standard errors of these estimates. So that's the first part of the question which we shall discuss right now. So basically you can understand that this is my population regression function which is actually unknown. We know and that there is a relationship between the variables y and x, but the coefficients alpha and beta are unknown. So this is the population regression function. Yi equals to alpha plus beta xi plus ui. And from this original population, you have basically taken a sample of size n. So naturally, when you're taking a small sample of size n, the most that we can do is to estimate these parameters alpha and beta on the basis of the collected samples, right? So therefore, we are going to estimate alpha comma beta by the OLS method, which we will denote it as alpha hat and beta hat. Okay, this is just a notation that we are going to use. So now understand this carefully, that this UI is what we refer to as a random disturbance term. Okay, that means a part of the yi can be explained by x and there is some small part of error that might be included. So before we actually go into the estimation part, we need to take certain assumptions on this unseen or unknown random disturbance term. So I'll just be mentioning those assumptions that are required for our computation purpose. There many more are there, but for our calculation purpose, these will be sufficient. So what are the assumptions that we need to take before proceeding with the calculations? The first assumption is that number one, the expected value of ui is equals to 0. Expected value of ui is equals to 0. This is the assumption of zero mean. Second, expectation of ui square is equals to sigma square. This is the assumption of homoscedasticity. That means the variance of the error terms are basically constant across all the observations. And finally, number three, expectation of ui uj is equals to 0 for all I not equals to j. This is basically the assumption of no autocorrelation. So what I mean to say is that this means that the error across the sample observations are not related. The errors are in some sense independent. So that is what I mean to say by expectation of ui uj is equals to 0. These are the important assumptions that we are taking. So now after we are taking this, then what will be the um, estimated regression function, which is the sample regression equation? So therefore the sample regression equation will be yi hat. The predicted yi will be simply alpha hat plus beta hat xi, because the error is unknown, and therefore hence the actual yi will be predicted yi plus an error. So let me label it as equation 1. Yi minus yi equals to yi hat plus ei, because a part of the uh, yi can be predicted with respect to the regression equation, and the another part will be the error. So now what we have to do, if we just go back to the question part A, we need to estimate the parameter alpha and beta by the OLS method and estimate the standard error of these estimates. So what do we do in OLS method? So therefore, so we are now in part A. We are starting with that formally. So what is error? It is basically yi minus yi hat. Okay. Now observe one thing carefully. We know that there is a relationship between y and x in the original population, which is given by the first equation that I have written. Yi equals to alpha plus beta xi plus ey. But alpha and beta are unknown. You are only observing that y. But you are trying to estimate yi hat by estimating alpha hat and beta hat. So yi you can't decompose into alpha plus beta xi because it's anyway unknown, but you will try to estimate these alpha hat and beta hat. So I can write it down in this way. In place of yi hat, I'm replacing this. Okay, so this is the expression for error. Now understand this, that if I square them up, then this is simply yi minus alpha hat minus beta hat xi whole square. And if I sum it up over all the observations I running from 1 to n, then this is the sum of squared errors. Okay, therefore, what is the idea of ordinary least squares? You will try to obtain alpha hat and beta hat by minimizing this thing, summation ei square. Let me denote it by s, by minimizing s. This is the fundamental idea of OLS. We will try to estimate the unknown parameters alpha and beta as alpha hat and beta hat through a technique which is OLS, which is basically minimizing the squared errors in this fashion. So now what we are going to do for minimization, we are going to take the partial derivatives of the s with respect to alpha hat and beta hat and set them equals to 0. So first, del s del alpha hat is equals to 0. So what do we get? The minus 2 comes in front. Summation I running from 1 to n yi minus alpha hat minus beta hat xi is equals to 0. So that basically gives us summation I running from 1 to n yi minus alpha hat minus beta hat xi is equals to 0. This is what we are getting. Now, if you just rearrange this a little bit, then we can write it in this way, keeping the summation yi on the left and taking the others to the right. So summation alpha hat minus beta hat summation xi, right? This is what you get. So, and if you just go a step further, summation alpha hat will be simply n times alpha hat and plus beta hat summation I running from 1 to n xi. This is what we get. And if you just divide it by 1 by n throughout, then what happens? 1 by n summation yi, and over here you will have alpha hat plus beta hat, taking the 1 by n with summation xi. So you get this. Y bar equals to alpha hat plus beta hat x bar. This is my equation 2 of the system. And now continuing with differentiating partially with respect to beta hat. So this will give me minus 2 will be out, summation I running from 1 to n, yi minus alpha hat minus beta hat xi into xi is equals to 0. So if you once again follow a similar step, keeping, so this will be yi xi this time, and this is equals to alpha hat summation I running from 1 to n xi plus beta hat summation I running from 1 to n xi square. Now over here I don't need to go for dividing by 1 by n because we don't have 1. So this is equation number 2. So now you can see we have two equations which are linear in alpha hat and beta hat, and we have two unknowns which is alpha hat and beta hat. So we can solve them out. Two equations, two unknowns can be easily solvable. So just I'm just rewriting. Therefore, the equations, these are basically known as the normal equations, are y bar equals to alpha hat plus beta hat x bar, and summation yixi is equals to alpha hat summation xi plus beta hat summation xi square. Okay. Now, yeah, as you know, this can be solved in many ways. It is basically solving a system of two variables and two equations. You can do it by any way. I'm just simply going by a simple technique. So by elimination, I can do it. So what we can do is that maybe now we can eliminate alpha directly and solve for beta. That is basically an easier way. I'll show you why. This you can just follow it up. So what we can do is that maybe I can multiply the first equation by summation xi and this by 1 and subtract them. So what will happen, you can see that this alpha hat will get multiplied with summation xi and it will get cancelled out. So that will make it much more easier, and you will subtract. So subtracting, what are we getting over here? So that will be y bar multiplied by summation xi is equals to beta hat summation xi into x bar minus beta hat summation I running from 1 to n xi square. This is what we are getting. So y bar, okay, sorry, I missed something. Just a moment. We are okay. Let me. Yeah. So this will be minus summation I running from 1 to n yixi, and that is equals to this thing. So that means y bar summation xi I running from 1 to n minus summation yixi is equals to, if you take the beta hat common, then you basically have x bar summation xi minus summation xi square. This is what we are having. So y bar, if you just extend it, it is 1 by n summation yi, and we had summation xi. I'm just not writing the summation I running from 1 to n repeatedly. It is making it more uh, look more cumbersome, so we can just drop it, not an issue. So this is summation yixi, and this is equals to beta hat x bar is 1 by n summation xi and another summation xi over here, so summation xi minus summation xi square. This is what we are getting. So now if you just simplify it a little bit more, if I just add another 1 by n over here, so this will go over here, another 1 by n over here, and 1 by n over here. So this will become, taking 1 by n with each of them, it will be x bar y bar minus 1 by n summation xi yi, which is equals to beta hat. This will become x bar square because the 1 by n will go inside the whole square, and that will become x bar and square it up. So this will be this minus 1 by n summation xi square. Taking the minus common and cancelling from both sides, it is 1 by n summation capital Xi and this x bar y bar, which is equals to beta hat 1 by n summation xi square minus x bar whole square. Okay. Now, if you remember one thing, that this is basically a simplified expression for covariance of xy. Okay, covariance of xy. So this can be basically written as 1 by n summation xi minus x bar into yi minus y bar. And this is the expression in the third bracket over here is basically a reduced expression for variance of xi. So that is basically 1 by n summation xi minus x bar whole square. So these two 1 by n's can cancel out, not an issue. So what is the final expression that you get for beta hat? It is summation xi minus x bar yi minus y bar divided by summation xi minus x bar whole square. Now it is often customary in econometrics to, so this, observe this part, what is xi minus x bar? It is the deviation of the observations from the mean, right? So it is often customary to denote them by small letters. So this is basically summation small xi yi by summation small xi square, where small xi is basically capital Xi minus x bar and small yi is basically capital Yi minus y bar. This is just a notation that helps us to make the understanding easier and calculation purposes. So now understand that when we have obtained beta hat, I can simply put this in equation 2, right? Therefore, now from equation 2, what is equation 2? It was y bar equals to alpha hat plus beta hat x bar. Now y bar and x bar can be easily calculated from the sample. So what is alpha hat? It is basically y bar minus beta hat x bar. So these two are your basically estimates of alpha and beta that you are going to obtain by using the OLS method. So this is the first part of part A, and the second part is we also need to estimate the standard errors of these estimates. Okay. So let me remind you something, that before we have computing the standard error, we need to calculate the variance. That is very essential, right? So first of all, we will go with calculation of the variances of these estimates, and then I'll show you how we are going to calculate the standard errors. So before actually writing the expression, let me just write down how we are going to calculate it. Like for example, like if I want to calculate the variance of beta hat, how do we do it? It is basically expectation of beta hat minus its expected value whole square. This is the way this is to be calculated. And similarly, variance of alpha hat will be expectation of alpha hat minus expected value of alpha hat, that whole square. So it's basically average squared deviation. That is basically variance. So for that, what we need to first obtain is what are these expected values. If we are not being able to obtain this, we can't replace them over here and calculate. Okay, so we'll first try to obtain that. So let us have a look at the expressions back. What is beta hat? It is summation xi yi by summation small xi square, where the x and y's are in small, right? So now have a look at this. The first thing that you can easily observe is this formula can be reducible. Let us say I keep the x in deviation form, okay, in small xi, but I now replace the y with the yi minus y bar. So if you just take a look at the numerator, what is it becoming? Summation small xi capital yi minus y bar summation small xi divided by summation small xi square. Now note this thing. What is this? Sum of deviations, which is 0, right? I hope you know this. So what is this becoming? It is becoming summation small xi capital yi divided by summation small xi whole square. Correct? So beta hat is basically, and just try to follow this step that I am writing. It is summation xi by summation xi square times yi. Okay, I have just taken the denominator inside and just taken the ratio as xi by summation xi whole square, and let us say I denote it as summation wi yi, where your wi's are basically xi by summation xi square. So one thing that we can observe from here, although they haven't told us to calculate, but we have to go through this way, so that we can actually obtain these variances first, that beta hat is basically linear in yi's. That means now you can write it in this way. It will become much simpler. Wi remains. What is yi? Yi is the original population equation that we are talking about. Alpha plus beta xi plus ui, right? So let me replace that. Alpha plus beta xi plus ui. So if you just replace it, what do you get? Alpha summation wi plus beta summation wi capital Xi plus summation wi ui. Okay, fine. So now we need to work out these expressions, summation wi and summation wi xi. So now note that what is wi? I have already shown you. It is small xi by summation xi square, and I need to calculate what is the sum of this expression, this thing. So this is basically, this sum can easily go in the numerator because the denominator is a constant and it can taken out. And again, by the logic that I just used, the numerator is 0, the sum of deviations, so summation wi is 0. So this part is basically not contributing anything. What will be summation wi capital Xi? It will be summation small xi into capital Xi divide by summation small xi whole square. So that is basically summation small xi capital Xi divided by small xi whole square. Okay, so small xi is capital Xi minus x bar times xi, and this will be summation small xi minus x bar whole square. So this will be basically summation small xi square minus x bar small xi divide by summation capital Xi minus x bar whole square. If you multiply the numerator and denominator by 1 by n, you can easily understand what this will be. So this will be basically 1 by n summation capital Xi square minus x bar whole square, right? Because 1 by n will go with summation xi and that will become x bar whole square. And on the denominator, you'll have 1 by n summation capital Xi minus x bar whole square. These two are essentially the same, right? One is the reduced expression of the other. So this is basically 1. So if you go back to this expression, which let me say it was star, therefore from star, what do we have? Beta hat is basically alpha hat summation wi. This part is 0, this part is 1. So this is beta plus summation wi ui. Correct? This is what we get. So now if you calculate the expectation, we can easily get it. So beta is a constant, so this will remain, and summation wi ui. So this is basically, I'm just writing this extra step, wi expected value of this thing. Correct? Now wi is basically in a component which depends upon x, right? And there is no assumption on it, and these are known values. So these are also to be treated as constant. So the expectation operator will only go on this because it's the unknown random disturbance term. And what is the assumption that we had taken at the very onset when we were starting? So have a look at this. Assumptions. Expectation of ui is equals to 0. That means this term is basically 0. So expectation of beta hat is basically beta. Right? So now for calculating, so what is variance of beta hat? Therefore, it is expected value of beta hat minus expected beta hat, that whole square. And we already showed above that what is the expected value of beta hat? It is beta. So we simply need to compute this expression, expectation of beta hat minus beta whole square. Now look at this term right over here, this equation. Beta hat minus beta will be simply expectation of summation wiui, right? And that whole square. So forget about the expectation part. How are we going to expand this thing? This summation wiui squared up. How are we going to expand this thing? So this will be expectation of summation wi square ui square plus double summation I not equals to j wi wj ui uj. Okay, so this is the expanded term that we are going to get over here. Now, if any of you are having any issue with understanding how we are getting this, please let us know in the comments. We'll elaborate on this a little more. But coming back to the expression that we are solving over here, so this can be further taken down as, so now this is what we are getting. So now by the similar logic, what I just explained in the last step, wi's are basically some component or terms of xi's which are known. So expectation operator will not be needed over there. So where will the expectation go? It will go over the terms with ui's, right? So the wi square will remain intact. It is expectation of ui square plus double summation I not equals to j. wi wj will again remain because they are simply in terms of this, and expectation of ui uj. Now if you again look at the assumptions that we have taken, then what is expectation of ui? That is sigma square. And what is expectation of ui uj? This is 0. The third thing that we had mentioned. Okay, so variance is basically sigma square summation wi square. All right, and now what is summation wi square. Wi square is basically, what is wi? Xi by summation small xi whole square, and that square. So if you just simplify this, it will be sigma square 1 by summation xi square whole square will come out. In the numerator, you'll have summation of xi square. So once it will get cancelled out, and you'll have sigma square by summation small xi square. Therefore, your variance of beta hat is basically sigma square by summation small xi square. So now what is the standard error? Now note something over here, that small xi squares can be easily computed from the data that you have in your hand, but sigma square is unknown. How are you going to calculate that? It's an unknown population parameter. So we again need to estimate this. So the moment I am replacing sigma square by the estimated sigma square, what is this becoming? This is becoming the estimated variance of beta hat. And if you are taking a square root of this thing, then that is basically the standard error. So what is the standard error of beta hat? It is basically the square root is basically some kind of, you can say, the estimated standard deviation, taking the square root of the estimated variance. So this will become square root over sigma hat whole square by summation small xi square. So that is basically sigma hat divided by square root, just a moment, divided by sigma hat divided by square root over summation small xi whole square. Now I'm not discussing in this video how you're going to estimate the sigma square, because they haven't asked us to prove the expression. But one thing is for sure, that if you want a completely computable value from the data that you have in your hand, all the parameters in which you are getting your expressions should be computable. But sigma square, since it's an unknown population parameter, you can't directly, you don't really know the value of it. So you need to estimate it using the data that you have. So in order to find the estimated variance, the sigma square needs to be replaced with sigma hat square. And this basically gives you the estimated variance of this estimated variance, and then we can easily get the standard error. Now I think you have understood the way in which we are going to proceed. So let me just go over this once more. First of all, with the original expression of beta hat that we got, we first showed that it is basically linear in yi's. And why we showed that, now you can understand, because that basically helped us to express beta hat in terms of beta plus something, and then using the expectation operator was much easier. So beta hat was coming out in terms of beta plus summation wi ui after the calculations, and from there the expectation was easily calculatable, and then variance was obtainable. Now we are going to follow the exact same steps for getting to the standard error of alpha hat. So first of all, how do we estimate alpha hat? I have just told you that estimating alpha hat is not of a hassle. The moment we estimate beta hat, we can easily estimate it as y bar minus beta hat x bar, right? This is already understood by you. So now just understand that we can always do a little tricks over here. Beta hat, we already showed you, that is a linear combination in yi's, right? wi yi's, correct? This makes sense. And y bar, you can easily write it as 1 by n summation yi minus x bar summation wi yi. Correct? So now understand this step a little carefully. Keeping the summation, if you take the 1 by n inside, that's also possible. 1 by n minus x bar wi, this whole thing times yi. Correct? And let me denote this thing as let's say some lambda I. So this is basically summation lambda I yi. So once again, what you essentially get is that alpha hat is basically linear in YIs. A pretty similar kind of a result that we are getting. Now again, since we are trying to get to the expectation first, so alpha hat is basically summation lambda I yi. And what is my original yi? Which is unknown. It's basically alpha plus beta xi plus uy. So that will be alpha times summation lambda I plus beta times summation lambda I xi plus summation lambda I uy, right? So once again, we need to get to these expressions. What is my lambda I? What is my lambda I xi? And what is the definition of lambda I? Let me just write it down once more. It is 1 by n minus x bar times wi. The wi that we have used in the computations for x beta hat. So therefore, summation lambda I, what will that be? It will basically summation 1 by n minus x bar wi, correct? So that is summation 1 by n minus x bar summation wi, correct? So summation 1 by n will be basically 1. And what is summation wi? It is 0, which we have already shown, right? So 1 minus 0, the answer is 0. Let me just write it down once more. That from our earlier calculation, summation wi is equals to 0 and summation wi xi is equals to 1. This we have already obtained, and I think we will be making use of these. So summation lambda I has been obtained, and now coming to summation lambda I capital Xi. So that is summation 1 by n minus x bar wi into xi. So that is summation 1 by n out, xi inside, minus x bar summation wi xi. So what is summation wi xi? This is 1, right? Which we have already obtained. And what is 1 by n summation xi? That is x bar. So x bar minus x bar, that is coming out to be 0. So just the opposite. Summation lambda I is coming out to be 1 and summation lambda I xi is coming out to be 0. So what is my alpha hat? It's basically your alpha plus summation lambda I ui. So alpha hat equals to alpha plus summation lambda I ui. So now if we take the expectation of alpha hat, alpha is a population parameter which is a given parameter, so it's constant, plus lambda I is basically, if you look at it, it's basically something in terms of x's only, because w is also expressed in terms of xi's. So that is also given. So the expectation operator will go over expectation ui only, and expectation of ui is 0. So expectation of alpha hat is equals to 0. Therefore, your variance of alpha hat is basically expected value of alpha hat minus expected value of alpha hat whole square. And we just obtained that my expected value of alpha hat is alpha. So alpha hat minus alpha. And from this expression, let me name it as double star in this case. What will be alpha hat minus alpha? It will be simply summation lambda I ui whole square. That's what is going to happen. So now, again, by exact similar way in which we expanded the earlier one, this will be expectation of summation lambda I square ui square plus double summation I not equals to j lambda I lambda j ui uj. And so the expectation operator will be going over only the ui terms. So expectation of ui squared plus double summation I not equals to j lambda I lambda j expectation of ui uj. Now again by assumptions, What is the expectation of ui square is basically sigma square, and expectation of ui uj was taken to be 0 by assumption. This will be sigma square times, okay, I missed a square over here, so summation lambda I square. So this is the expression for variance of alpha hat. So now what the only thing that remains is computing this expression. What exactly is my summation lambda I square? So let's get back to it. So what is my lambda I? It is 1 by n minus x bar wi. This is what it is. So what is lambda I square? If I can just obtain it before taking the summation, it is 1 by n square plus x bar square wi square minus 2 into 1 by n x bar wi. Correct? This is what it is. So now if you take the summation, so summation lambda I square, so what it will be? Summation 1 by n square plus x bar square out summation wi square minus 2 by n into x bar out summation wi. Now what is summation wi? This is 0. We already know this. So what is it coming out to be? So summation lambda I square is basically, this will be n times 1 by n square plus x bar square summation wi square. Okay. So now if you look at the expression, we have already calculated summation wi square as well. Just a moment. Yeah. So summation wi square is basically your this part. 1 by summation small xi square, right? From here, from this expression over here. Sigma square is out and summation wi square. So the calculation that is involved showed that summation wi square is basically 1 by summation small xi square. So summation wi square is equals to 1 by summation small xi square. So we can easily substitute it over here. So summation lambda I square equals to, this will be just 1 by n plus x bar square into 1 by summation small xi square. Okay, so if we can maybe take the LCM to get a simplified structure, so it will be summation small xi square plus x bar square times n divided by n times small xi square. This is what it is. So summation small xi square, I can just replace it in the capitals to check if we can get a further simplified situation. X bar square will be what? 1 by n square summation xi whole square. So 1 n will get cancelled. And then we basically have summation capital Xi minus x bar whole square plus 1 by n into summation small xi whole square. Right? And the denominator remains unchanged. Now if you just go over this thing, the first term summation small xi minus x bar whole square, this will be basically summation capital Xi square minus n x bar whole square plus n x bar whole square divided by n times summation small xi square. So these two will get cancelled out, and you basically have summation capital Xi square divided by n times summation small xi square. So this is the expression for summation lambda I square. So we'll simply replace it. Therefore, variance of alpha hat is basically sigma square summation capital Xi square divided by n times summation small xi square. So the estimated variance will be simply replacing sigma square by the estimated value of sigma square, and standard error of alpha hat is basically the square root of this estimated variance. So that is basically sigma hat times square root over summation capital Xi square n times summation small xi square. So this completes your answer to part A of question number 2. We shall continue with part B in the next video. Thank you.